Learn like a pro.
So, let's talk about an invisible force that's all around us. You know, that little shock you get from a doorknob? That's static electricity. But what if I told you that same exact principle is used to clean the air we breathe and to give cars that perfect glossy finish? How does one idea cover everything from a tiny zap to massive industrial tech? Well, let's get into it.
Okay, I know that sounds like some kind of weird riddle, right? But the answer connects these two completely different things with one single, really powerful scientific idea. And we're going to unravel this whole mystery by starting at the very, very beginning, at the smallest scale you can imagine.
To get a handle on how all that big stuff works, we've got to zoom way, way in, all the way down to the atomic level, because that's where you'll find the one simple rule that runs this entire show.
Yeah, everything from scrubbing factory smokestacks to getting a perfect coat of paint on a car door, it all boils down to this one fundamental truth.
Seriously, that's it. That's the whole game. See, in an atom, you've got these positive protons, and they are locked down tight in the center, in the nucleus. They're not going anywhere. It's only the tiny, negative electrons buzzing around on the outside that can actually jump ship from one object to another. And that simple fact, it's the key to everything else. So just picture it. You've got two surfaces rubbing against each other. Some of those little free agent electrons get torn away from one surface and pile up on the other. This means the first surface is now missing some electrons. It has these little vacancies, which gives it a positive charge. And that right there, that's static electricity. It's not a current. It's not flowing like the electricity in your walls. It's a charge that builds up and just sits there. That's what static means, unmoving. It's just a pileup of negative charge on one thing and a matching pileup of positive charge on another. Now you might be thinking, this whole electron swapping business is pretty random. But it turns out it's not random at all. In fact, it's incredibly predictable. It all comes down to what the materials are actually made up of.
And the first big thing to know is the difference between insulators and conductors. In insulators, think wood or plastic, the electrons are basically glued in place. They can't move around freely. So the only way to charge them up is with friction. You literally have to physically scrape the electrons off. But in conductors, like metals, the electrons are like a big roaming mob. They can move anywhere inside the material, and that opens up a whole different way of charging things up. So for those insulators, how do we know which way the electrons are going to jump? Well, we just check the electrostatic series. It's basically a cheat sheet that ranks materials on how easily they give up their electrons. Stuff on one side holds on tight, while stuff on the other side, well, they're pretty generous. Let's make this super clear. Let's say you rub a polythene rod with a cloth. The series tells us the cloth gives up its electrons easier, so they hop over to the rod. Boom, the rod is now negative. But what if you swap that out for an acetate rod? Well, the chart shows that acetate gives up electrons even more easily than the cloth does. So this time, the electrons jump from the rod to the cloth. And just like that, the rod is left with a positive charge. See? Totally predictable. Okay, so what about those conductors, the ones with the free-roaming electrons? This is where things get really, really cool. You can actually give them a charge without ever touching them. It's a method called induction, and it's kind of like magic. Induction is all about influence from a distance. You bring a charged object near a neutral conductor, you don't even touch it, and its electric field reaches out and pushes or pulls on all those free electrons inside. It basically sorts the charges within the object, all without making any physical contact. Here's the four-step dance. First, you bring a negative rod close to a neutral metal sphere. All the free electrons inside the sphere get repelled and run to the far side. Second, you give them an escape route. You connect the sphere to the ground. All those crowded electrons immediately flee down that path. Third, and this is the most important part, you remove the ground connection while the rod is still there. That traps the remaining positive charges. And finally, you pull the rod away. What are you left with? A sphere that has a permanent positive charge. It's just elegant. All right, so now we know the rules of the game. We can create charge by rubbing things together, and we can move it around with induction. So, what happens when we take this fundamental force of nature and actually put it to work? Let's see how we turned it from a party trick into a super precise, powerful tool. Remember that riddle I started with about the clean chimney? Well, here's your answer. This is an electrostatic precipitator. It's a giant device that uses static electricity to literally pull pollution right out of factory smoke. So here's the play-by-play. The dirty smoke enters the chimney and flows past this negatively charged metal grid. As the little bits of soot and ash pass by, they get zapped with electrons, giving them a negative charge.
Then, these now negative particles are pulled towards big positively charged plates. They stick to them like magnets. Every so often, the plates get shaken, the dirt falls into a bin, and what comes out the top of the smokestack? Clean air. It's a giant static-powered filter.
And that brings us to the second half of our riddle, that perfect paint job. This is the same exact science, just on a different scale. It's what gives cars that flawless, almost liquid-smooth finish, and it does it with almost no wasted paint.
Now this is so smart because it uses two principles at once. First, as the tiny paint droplets leave the sprayer, they're all given a positive charge. And what do like charges do? They repel. So the droplets push each other apart, creating this incredibly fine, even mist. At the exact same time, the car body panel is grounded, which makes it super attractive to that positive paint. So the mist doesn't just drift onto the car, it's actively pulled toward the metal, wrapping itself around every corner and edge. It's unbelievably efficient.
But it's not just about using this force. It's also about managing it when it becomes a problem. Think about an airplane. As it flies through the air, all that friction builds up a massive static charge. If that charge gets too high, it could interfere with navigation and communication. So planes have these little things called discharge rods that safely bleed that static charge off into the air.
So when you think about it, from a sock sticking to your shirt to painting a car with almost zero waste, it all comes back to that one simple idea. Only electrons move. By figuring that out, we learned how to control an invisible force and use it to shape our world. Control the electron, you control the whole system. It really makes you wonder, what other invisible forces are just waiting for us to figure them out?